Polymers have long been around, much before we started synthesizing them, occurring in nature, for example, in DNA, proteins, cellulose, and much else. However, ever since the fairly synthetic polymers of the early 19th century, synthetically man-made polymers have become increasingly ubiquitous in technology in modern science. As such, they've had a huge impact on our lives, many being revolutionary in modernizing how we live our lives. With these positive uses, there has also been some negative impacts, and the focus of this presentation is one of the responses to one of the major negative polymer impacts. But to start, what is a polymer? Polymers are large molecules made up from small repeating units called monomers, linking up in a chain-like fashion. So in this example, polystyrene, the material is made up of these polymer chains. But if we look closely, the chain is just this bottom species repeated lots of times. Lots of these polymer chains come together and make the material overall. The overall material's properties are determined by the structure of these chains, specifically the backbone and branching structure. The backbone structure is the central chain of atoms that runs through the structure and connects the polymer up. Here, the backbone structure is carbon single bonds, but it could also contain peptide bonds, aromatics, and double bonds, and many different combinations of functional groups. The other factor in determining polymer properties is branching structure and branching functional groups. These are the atoms that don't make up the central backbone, but come off like a branch. Here it is just hydrogens, but we can also have larger and longer branches on many different functional groups. With different combinations of backbone and branching structures is what gives us the many advantageous properties of polymers. As such, there are many useful applications and places polymers have been implemented, like in medicine, either as implants or to reduce side effects, in electronic devices, being used to store energy as screen displays or being used in solar panels. This polymer is an example of such, and we can see how its conjugated system allows electrons to move through the polymer chain. The polymers are also used in plastics. Polymers can be made into durable, lightweight, and flexible materials. As such, they have been used in packaging, construction, and consumer products, as well as much else. Here is an example of one plastic, polyethylene. Due to only carbon-carbon and carbon-hydrogen bonds present, it is a generally unreactive species. There is low-density polyethylene. The increased branching structure means intermolecular forces are reduced and gives a material with less tensile strength, whereas high-density polyethylene, the reduced branching structure allows chains to get much closer, giving a stronger material overall. Polymers clearly, thus, have had many advantages, seen by their many applications and explained by their structure, but they also have had disadvantages. Continuing with our example, what makes polyethylene and most plastics so useful is their unreactivity, but this also means they don't degrade easily and accumulate in landfills and the ocean. Furthermore, polyethylene produces greenhouse gases when it does break down, further harming the environment. It has even been estimated that every year, 25 million tons of plastic ends up in the ocean. And hence, there has been a rise in research for biodegradable polymers, which won't have these same negative environmental impacts. The basic principles of biodegradability is that enzymes or chemical deterioration can break down the polymer after use, for example, by hydrolysis. Here we can see H2O molecules breaking the polymer down at the ester linkages. There's been some successes in the science of these polymers, and such they've been implemented in packaging and as single-use plastic alternatives. PLA is used in cups, bottles, and film. We can see, just like in our previous example, it contains an ester linkage, explaining its biodegradable properties. PLA and its co-polymers have also been implemented in biomedicine as implants due to its biocompatibility and biodegradability. PLA is also made from lactic acid, the most widely occurring hydroxyl carboxylic acid in nature. PLA is useful because not only is it biodegradable after use, but it's made from lactic acid, a renewable source. It's the potential to replace petrochemical polymers for almost all pharmaceutical and direct food contact packaging. It is not yet 100% green process due to chemically derived methods of synthesis, but has great potential and is already providing to be a viable alternative. So overall, polymers have had many advantages and still do, and we owe much of our modern day advancements to them. The issue of polymers is that they are so useful and widespread that environmental impact has become quite serious. Biopolymers provide an alternative and viable solution, but much work still needs to be done. For example, non-water soluble biodegradable polymers often end up in dry landfills, showing that there is progress, but still more needs to be done.